Hello and welcome to Predictions of Quality Red Wine with R. My name is Jimmy Herr. A little bit of introduction and background into my project. It showcases a restaurant named Jimmy's Wine and Steak, which is a well-known and established steak restaurant that offers premium steaks with quality restaurant experience. Now, in an effort to maximize profits and sustain market share, management has requested for a quality red wine to be offered with its quality steak selections. As with understanding what makes a good quality steak, the desire here is to understand the proper inputs that go into making a quality red wine. Therefore, a predictive model will be initiated to predict quality red wines based on physiochemical characteristics. Now, the proper presentation for Jimmy's Wine and Steak includes a shift in customer purchases to lower tiered options. Additionally, we've also seen that there's been emergences of new competition within the fine dining market. Competition and losses on both these fronts have led to lower profit margins and a decrease in the market share. The decision has been made by management that this business environment will not be sustainable for Jimmy's Wine and Steak in the long run. Therefore, there needs to be some kind of enhancement to the experience at Jimmy's Wine and Steak. This enhancement will come in the form of a quality red wine selection that can be offered to complement its steak selection. To begin the project, data was needed and acquired via kaggle.com or the UCI website as showcased in this slide. In the data exploration section, the first line of business was to analyze and understand the predictor variables. A high-level summary was considered of the individual graph plots of the histograms and also a box plot of all predictors. As you can see here, as an example, the fixed acidity histogram is shown on the bottom left, and a box plot presentation of all predictor variables shown on the right-hand side. The second line of business for the data exploration section was to analyze and understand the relationships between the predictor variable and a dependent variable quality. To achieve this, a correlational matrix plot was graphed. This correlational plot actually shows the degree of interrelatedness between the variables. An example of this is shown on the next slide here. And as you can see, the darker color or larger size circles actually represent more correlation between the variables. The blue color indicates positive correlation, whereas the red color indicates negative. There are 5 predictor variables that are showcased here that show a medium to high rating with quality. And specifically of these 5 variables, volatile acidity and alcohol showed the most correlation with large and dark colored circles. Worth noting in this correlational plot was that there existed some strong correlations between predictor variables indicating a potential for collinearity. An example of this is showcased with the citric acid, which has strong correlations with fixed acidity and volatile acidity. In summary, for the data exploration section, the individual analysis of the predictive variables did not provide very much insight. However, the correlational analyses of variables did provide useful information. Furthermore, in the data transformation section, there were no NA nor no values in dataset. The UCI dataset required no cleaning and all values were numerical. Conversely, we did notice that there was some variance in the index values between the predictive variables that we would deal with through normalization. Now, to address this issue, the dataset would be split into a train and test set. The train would be about 75% and the test would be about 25%. And after it's been split, then secondly, it would be normalized to the same range. Normalization is necessary for predictive model usage and interpretability so that the results are standardized to the same range. Here showcased is a summary of all the data before normalization. Now, as you can see, we have values anywhere ranging from about 0 to 289, which makes for comparison to be very unfeasible. Showcased here is a summary after normalization for the training set. Now, as you can see, predictor variables are only from 0 to 1, making for easy comparison. And similarly to the train set, the test set here after normalization showcases values from 0 to 1, making for easy comparison. In the specification, design, and theoretical motivation section, before we begin, let's recap a little bit from the data exploration section, which showcases a poor linear relationship between predictors and the dependent variable quality. Collinearity does exist between the predictor variables, and taking into account these two notions would mean that we would violate the assumptions of the linear model. Now, although the linear model is unfit for the quality red data set, it does provide a good starting basis to understand the data set to plan for more fitting predictive models. And to confirm or deny the theory that the linear model will not work sufficiently for our data set, the linear model will be executed to analyze. Now, to start the process of linear regression model, feature selection was performed to fine-tune the model to decrease the variance. And this is important as there may be many predictors that may not contribute to the dependent variable response. The lasso method was chosen as the feature selection due to its ability to actually shrink the irrelevant predictors to 0. Additionally, it works well with a small number of predictors. To begin the lasso process, the lambda term needed to be determined, which is shown here. And shown here is execution of the lasso query. Outputs from the lasso are shown to the right, and here are the three variables that are chosen: volatile acidity, alcohol, and sulfates. The linear regression model will be deployed with three lasso chosen variables as predictors. And the strategy moving forward will depend on the outcomes of the linear regression model. If results are good or sufficient, then other linear models will be entertained, such as your principal component, polynomial, or step functions. However, if we are provided with not sufficient results, then the classification methods, such as your support vector or random forest, will be entertained. In the iterative results section, the multiple linear regression model was tested in two scenarios, one with all 11 predictors and one with just the three lasso chosen predictors. Metrics for the model quality were lower for the three lasso scenario. The results showed a decrease in adjusted R value at 0.3301. The p-value was similar, but the F statistic increased. These results were anticipated as a decrease in the number of predictor variables would decrease the adjusted R value. Showcase here is the multiple linear regression model with all 11 predictors. And here, multiple linear regression with the three lasso predictors. Now moving on, we did want to entertain the polynomial regression model. And that is the next step in this iterative model selection process. We will consider the quadratic, cubic, and quartic to compare all three results to deduce if the polynomial regression model is sufficient for the quality wine dataset. Here showcase is the quadratic fit with the standard error of 0.72354. Here showcase is the cubic fit with the standard error of 0.72117. Quartic fit here with the standard error of 0.72147. Now here's a comparison of the three polynomial models with the ANOVA function. And the ANOVA table showed that the quadratic fit is insignificant, whereas the quartic fit had a high p-value, thereby making the cubic fit the most feasible with the p-value at 0.002985. And a quick analysis of the standard errors for each polynomial model indicated values at 0.72 plus or minus 0.001. The standard error decreased as the model expanded to the cubic fit, but did not decrease further to quartic. As noted in the ISLR text, a further increase of the polynomial fit power does not guarantee a decrease in error. In summary, for the polynomial models, the cubic function compared better than the quadratic and quartic. The overall consensus for the linear models, including multiple and polynomial, is summarized by a higher than desired standard error and low adjusted R-squared values, making them insufficient for the quality red wine model. Therefore, moving on to the classification models, our next phase in the iterative process was to test the classification models of random forest and support vector machines. First off was to run the random forest, and here the strategy was to employ a model with the lasso chosen variables, and then do the 11 predictors. The first run of the random forest is shown here with the lasso variables, and the mean square residuals for the random forest lasso run gave 0.394. To further investigate the potential of the random forest, the next run included all 11 predictors with the k-fold cross-validation. The cross-validation is a resampling technique to avoid overfitting of the model. And specifically in our case here, we ran a 10-fold cross-validation. The second run of the random forest shown on the next slide here with the 10-fold cross-validation in all 11 predictors shows a final value for the MTRY equals 3. The root mean squared error for the final value at a 0.582 with the mean squared error at 0.339. R squared at 0.485 and a mean absolute error at 0.435. As you can see here, the performance shown with the cross-validation does better with the lower error output at 0.339 versus the 0.394. The cross-validated random forest model was plotted below to actually showcase that 3 variables contributed to the lowest RMSE of 0.5821. This supports the notion that approximately 3 variables are relevant to the response of the dependent variable quality. Now moving on to our next classification model of SVM or support vector machines. Here, similarly, we run a 10-fold cross-validation. And specifically for the SVM, the radial basis function kernel was run, which is highlighted below here. In the summary comparison figures that will be shown on the next slide, the respective MSE and MAE for random forest are lower than compared to the SVM. Additionally, the R squared is higher for the random forest model. With all considered, random forest is the best fitting model for quality red wine dataset. Here's a comparison figure again for the SVM versus the random forest. And here's a description of the results. The random forest model has shown its performance advantages and subsequently will be implemented for the quality red wine dataset. The strategy will be to employ 2 setups. One setup will train and test without cross-validation, while the other setup will train and test with cross-validation. The training plan will consist of 4 separate runs with a 10-fold cross-validation. Here a showcase is the random forest training run number 1 without cross-validation. This was repeated 3 more times to train 4 times total. Here showcase is the random forest test run without cross-validation and the respective MSE and MAE of this RF test. Now showcase here is the random forest training run number 1 with cross-validation. This was repeated 3 more times to train 4 times total. Here's the output for the random forest test run with cross-validation and its respective MSE and MAE. Here showcase is a summary diagram of the random forest versus the random forest with cross-validation. And as you can see, the random forest with cross-validation outperforms with the lower MAE and MAC. The conclusion of the results of the project showed that the random forest is the best model predictor for the quality red wine dataset. As mentioned, there were only 3 relevant predictors that contributed or correlated well with quality. This does not bode well for the understanding that constitutes a quality red wine, as the desire was to have more than three relevant predictor variables. In retrospect, perhaps only two of the relevant predictors were true predictors: volatile acidity and alcohol. This is aligned with the notion of contributing factors to quality red wines. As wine ages to attain quality, they offer a more stable alcohol content and refinement in taste, both of which are resulting outcomes of volatile acidity and alcohol. The alcohol content correlates well with quality, but is not giving any indication or direction on whether a higher or lower alcohol content equates to more quality. And unfortunately, this is due to the narrow range of resulting alcohol content. Therefore, determining quality red wines would not be attainable with the knowledge of alcohol content. As for the volatile acidity, the assumption is that taste is affected by this predictor variable. Perhaps with age and refinement, volatile acidity is decreased, thereby allowing for a smoother taste with less extreme hints of sourness and bitterness. Some final considerations for the project include, instead of the physiochemical properties from this data set, perhaps sensory variables that wine testers or tasters base their quality ratings on may be of more value. In regards to improvements that can be had with this modeling project, include more fine-tuning of the models and explorations of other classification models or more models in general. Again, thank you for your time.